basically with a small recap of what we did last time. So remember that I started out with a matrix, let's say real symmetric. And we said we are looking at the rotational invariant ensembles where you have a joint distribution of these matrix elements, n by n matrix. And so this, for instance, we took something of, in general, something of this type. I'll just put a beta factor here in just okay. So this Vx is a polynomial potential, and in particular, if you just take the quadratic, then it just becomes Gaussian. Okay, otherwise, you can consider the general potential like that. And then we said, okay, we diagonalize this matrix. This was the first step. And you go to the change of variables, you go to the lambda n's and the eigenvector degrees of freedom. Okay. And so you write down the joint distribution of all these observables, and then you integrate out the eigenvector degrees of freedom, and that gives you, finally, the joint distribution of the eigenvalues, which has this generic form. So this is just a normalization constant because the total integral over all the lambdas should be equal to 1. Okay? And then this part just transforms in terms of eigenvalues as you just replace v of x by v of lambda I and sum over all I, okay? Because the trace is invariant, so therefore this is just this object. But when you do this change of variable, you get this extra Jacobian factor, which was, let's say, j less than k. Where we said that for depending on the ensemble, real orthogonal matrices beta equal to 1, unitary matrices beta equal to 2, complex summation matrices, and then quaternion matrices beta equal to 4. So this is the Dyson index. However, we said that in general, once you have this, you can think of this beta as a continuous parameter, not necessarily just the 1, 2, 3. And there are matrix models which do give rise to a general arbitrary beta. This is the Dimitru-Edelman matrix, okay? But, okay, and this beta is important here, the power of the Vandermonde term, okay? But this beta here, I just put in by hand because it's just a constant, so I can put it anyway. And the reason I did that, so that I can write down this as 1 over Zn. This is not very important, but you can just put it, just rescale all the lambdas and write it this way. So this I can write down as exponential minus beta, okay, beta by 2 if you like. So let me put beta by 2, and then E of summation lambda I, where the E of summation lambda I is simply just summation I V of lambda I minus log lambda j minus lambda k, j not equal to k. Okay? So once you have that, so this is going to be the further, so this was the first step to derive this distribution. And so the second step would be to start from this and subsequently proceed to calculate these things. So once you have come to this stage, okay, so then you can actually forget about your original matrix now. Okay, I can just deal with a gas of eigenvalues, which are denoted by these positions. Their positions are denoted by lambda 1, lambda 2, lambda 3, lambda n. And so basically what we have here, as I mentioned, that I can interpret this system as a set of charged particles. These are not real particles, they are eigenvalues. Okay? So these eigenvalues, so I can interpret these as the probability distribution of the configuration. So this is exactly critical, this is exactly equilibrium statistical mechanics. You remember that Kiran wrote down in the first lecture that in equilibrium statistical mechanics, whatever be your system, this is a configuration. So for example, the Ising model is a spin configuration. In this case, it's a configuration of the lambdas. So in equilibrium statistical mechanics, you always write down this. This is the Gibbs measure as exponential minus beta, or beta by 2 if you like, doesn't matter really, and the energy of the configuration. Okay? So this is the prescription of the equilibrium statistical mechanics. So this is the Gibbs measure. Okay? So in Ising model, you have a particular type of interaction, which was in Ising model. For example, in 1D Ising model, you have energy of a spin configuration, which are +1 or -1. So this is just minus j summation si plus 1. Okay. So in Ising model, this was energy is actually the only local interaction, nearest neighbor interaction between spins. So you have this bunch of spins on a line, on a lattice. So this is a typical spin configuration. And so each pair of nearest neighbor spins, they actually contribute. So they like to be parallel to each other. Okay, then you get a contribution to energy which is minus j. But if they are anti-parallel, then you get a plus j. Okay? So this is the Ising model. So Ising model with short range interaction. Okay? So similarly, think of here, we have a equilibrium system of particles with positions lambda 1, lambda 2, lambda 3, lambda n. And this was a mathematical derivation of the joint distribution. And after I have done that, I can interpret this. These are not real particles. I can interpret them as if that they are given by an equilibrium Gibbs-Boltzmann distribution, exactly like this. Okay, these two, I just took it out as a convenience. And with an energy which is given by this. So what is in the energy, there are two terms. So there is this term here, which is typically like Gaussian case, V lambda is, so Gaussian is, V of lambda is just lambda square. Okay. But you can think of other potentials. So in general, this should be a confining point. Potential has to be such that this distribution should be normalizable. It should be normalizable to unity. So you can't take any arbitrary potential. It typically has to be confining potential like that. So this confining potential is trying to push the charges towards the center of this potential. But in addition, there is a second term, which is the interaction term. So if you didn't have this term, there will be non-interacting. It's like putting a spin in Ising model. So if you put a spin like this, so if j equal to 0, then you see that the energy just decouples. It's the sum of the individual spins. They don't interact with each other. Okay. So similarly here, the analog of this guy will be here. So if I did not have any interaction between them, then they'll just decouple. There will be some energy will be the sum of the individual potential basically. Okay. But now, analog of this term here is this interaction term. Okay. So this interaction, but is different from the Ising model in the sense that in the Ising model you have a short range interaction. Only nearest neighbor spins or particles they interact. But here, it's actually a long range interaction. So long range in the sense that any pair of particles, if I pick any two pairs, okay, there is a term which is the log of lambda j minus lambda k. If I take any pair of j and k, there is a repulsion term here, which they repel each other. And in particular, when they are close by, the repulsion is stronger. Okay? So they like to push away from each other. Okay? So there is a competition between these two terms here. And so this is so now we can actually forget about the matrix. I mean, actually at this stage, I've already integrated over the eigenvector degrees of freedom. So I cannot go back from this knowledge. I cannot go back and reconstitute any knowledge of the matrix because I've already integrated out certain degrees of freedom. Okay, so we can forget about matrix actually. Now we are just thinking of only eigenvalues. Okay, so I'm focusing myself only in the eigenvalue sector and interpreting this as a statistical mechanics of a gas of particles. Okay, we would like to now derive some equilibrium properties given. So it's like a standard StatMech problem now. So you have some, your energy is specified for each configuration of lambda i's, and then you want to calculate some properties. Okay. So that's the program. Okay. So from now on, it's only statistical mechanics. Okay. Now, as Kiran told you, that a 1D Ising model is very easy to solve. All of you have done that, I suppose, by using transformatic techniques. Okay? And the reason you can do that is because there is a short-range interaction. Okay? It will not work if you have a long-range interaction. Okay? So we cannot use just simple transformatrix techniques to solve. So here you remember that this Zn is just a normalization, but this is like in the Ising model. Okay? So Ising model also, when you write down this Zn, it's a partition function. So in the Ising model, the partition function is sum over all spin configurations times exponential minus beta, because sum over all configurations C should be equal to 1. So that fixes that Zn should be equal to over all spin configurations. Okay, so this is you can solve by transformatrix techniques. So here similarly, I have this partition function, which is sum over all possible lambda i's, since lambda i's are continuous variables. So you have a multiple integral to do here, all going from minus infinity to plus infinity. And then I have this e to the power minus beta by 2 e of lambda I. So I need to calculate the partition function, and after the partition function, but it's not just the partition function. I want to calculate, for example, the average density of states, which I defined last time, okay? And so on, and that's what going to be today's program. How do we calculate that? We cannot use transform matrix, so how do we calculate that? Okay. Now, it turns out that for the special case of Gaussian potential, okay, this horrible n-dimensional multiple integral, you can actually do it exactly. And this goes by the name of Selberg integral. Let me just say the result. I will not prove it, but I want to keep this picture, so maybe I don't know. Okay. I'll just write it down here. Okay. So, special case. So this multiple integral Zn, which is what I wrote down there, this object here, with v lambda equal to lambda square, and then you have this interacting term. Okay, let's just write it explicitly again. Okay, so you have this multiple integral. In general, physics is all about solving integrals. Okay, so this integral is hard to do. Okay, but it so happened that for this particular special choice of the potential, so this integral is exactly known. So I'll just write down the result without trying to prove it. This is 2 pi to the power n over 2, beta to the power minus n over 2, minus beta over 4, n into n minus 1. Times this gamma function of 1 plus beta over 2. You'll see it's horrible actually. And then your product of gamma function. This is an exact result for all n. Okay. And so this goes by the name of Selberg integral. Selberg is a guy who actually solved a lot of multiple integrals. That was his job basically, and he was very good at that obviously. It's highly non-trivial to prove this. Okay. So, so for that particular case, you can actually calculate. So this is an exactly solvable model, okay, for all n. And from this, you can then take the large n limit because that's typically the limit we are interested. So, okay, so you find that log of Zn, which is like the free energy, so that goes in the n going to infinity limit as beta over 4 log n times n square. So there is a term which is n square log n, leading term. And then you have this beta n square 3 over 8 plus 1/4 log 2. So you might say that, okay, I mean, everything is known, everything is done, so what do I need to do more? The problem is that this is just this Zn, okay. If I want to calculate even the average density of states, because as I told you that these charges are so always remember this physical picture, okay, that you have this line and you have this confining potential, whatever it is, and you have these charges sitting there in this potential. And there is a confining potential V of lambda, and the energy of this configuration is just 1 minute, Sorry? No, this is the point, because it's a long-range system. See, the energy, I'll come to that in a minute. You'll see why n square is quite normal. Because, you see, it's a pair potential. How many pairs are there? N into n minus 1. No. So no. Even if you do that, it will be always n square. If changing coupling constant, you cannot. The overall energy is always going to be order n square because of the long-range pair potential. So in that sense, this is very different from the standard StatMech system. This is a 1D long-range system. So long-range physics is actually quite often different from short-range physics, okay, as we'll see. Okay, so so what I want to now calculate is, so as I said, there's a competing interaction. So there's a confining potential and there's a logarithmic repulsion. Okay. So this guy is trying to push the charges towards the center. They are trying to repel. So finally, they will settle down into some kind of average density. There will be more particles here and less particles as you go away. And we want to calculate this average density of states, density of particles. So to define that, you can define something like this, which is a counting function. So what is this object? So this object tells me that there is a contribution only when as I vary lambda, whenever there is a charge, it picks up a delta function contribution. So this is the density, because if you normalize to unity, so if I integrate, for example, this guy, so you get 1 over n. So when I integrate over d lambda, this gives 1. So n cancels, so this is 1. So this object is normalized to 1. And so this is called the density of states. So for any given configuration, I can define this object. So this object is a random variable in the sense that it's changing from one configuration to another configuration to another configuration. And what I want to calculate is the average density of states, because that will give me the idea of how they are settled in this potential. Okay? So which is just the first moment of this, so expectation value of rho and lambda. Sometimes I will not write this bracket, so this means that's just average value. So average rho and lambda is just the average, and this average angle bracket means averaging with respect to this Gibbs measure. Okay. sometimes I will not write this explicitly as the average value. I mean, like, but you will understand I'm talking about the average value. In fact, what it turns out that in the large n limit, in fact, this average value, I mean, the random variable tends to a delta function with mean, with peak around this average value. So rho n lambda tends to, tends to a constant in the sense that not a random variable. It has a delta function measure basically, and we'll calculate the average density. But for the moment, let's just think of the average density. Now, if I want to calculate this average density, knowledge of partition function is not enough. So again, it's unlike in the Ising model, where if you know the partition function explicitly, you can calculate the free energy and you can calculate the other things. But as Shumit was telling you that if you want to calculate the correlation function, you usually have to put a field here and then take derivative with respect to field to calculate the correlation function and so on. Okay, so same thing here. If I want to calculate this average density of states, I have to somehow put a field or something, and then unfortunately the Selberg integral doesn't work. Okay. So even though this is, and also other problem is that this is particular for the Gaussian case when the quadratic potential, but for other potential we do not know the exact formula. Okay. So therefore, we need to develop a way to at least get the large n result without knowing Selberg integral. Okay. So we want to set up some way so that we can understand for any arbitrary potential. Okay, and as well as we should be able to calculate observables like the density of states. Okay. So how do we do that? So the idea is then to set up a field theory for this problem. Okay. So you have a 1D long-range system with n particles, and what I want to do is to set up a field theory for this. Okay, and you will see that this field theory in the large n limit will give an answer automatically, very nicely, and that's the sort of plan. Okay. So the lambdas. So you ask, first thing you ask, just a dimensional analysis, that what's the typical value of lambda? How does it depend on n? This is a good exercise. So you see, this guy, first term, how does it scale with n? So if a typical value of lambda is lambda typic, so there are n such term here. So this term, the estimate of the first term will be n times lambda typic square. Okay. So this is the first term. What about the second term? Second term, as I said, that there is a contribution from each pair. Okay? Each pair. So how many pairs I have? If I have n charges, I have n into n minus 1 by 2 distinct pairs. Okay? So which in the large n limit will go like n square over 2. Okay? So there is a order 1 contribution, let's say, from each term. Okay? Typically, I'm just estimating typically. Okay? So therefore, this term, second term, typically is of order n square. So in order to obtain, the system will go into a, typically such that both terms will contribute. Okay? So which means that these two, which at equilibrium, these two energies will balance each other. Okay? So therefore, this object first term should be same order as the second term. Okay? So you cancel 1 power of n. So this gives you that lambda typical scales like square root of n. Okay? For example, if you just take this matrix and diagonalize and calculate the, so imagine you are doing simulation. Okay? So you calculate the lambdas, the eigenvalues, and you just plot look at the typical eigenvalue. You will see that as you increase your system size, matrix size, it typically scales as square root of n. Okay? So one thing that people do is that because it's scaling like square root of n, so right in the beginning I know that it's a square root of n. So if I want to work in the convention that lambda typical is of order 1, what I should do is to rescale these lambdas. Okay? So I can call this lambda I, because it's of order square root of n, I can define a new set of variables, lambda I twiddle. Okay? So So if I do that, so then you get a factor n outside here. So in terms of lambda I twiddle, I can rewrite this partition function. Okay, so there will be overall factor which I don't care. Okay. This is just done for convenience. So this becomes n times lambda twiddle I square. I just made a change of variable, rescaling. And here, when I do, replace lambda I by lambda I twiddle times square root of n, so you see that so this will be log of square root of n times lambda j twiddle minus lambda k twiddle. And because it's a log, so it separates out, it becomes half log n plus log of this lambda j twiddle minus lambda k twiddle. Okay. And again, this overall factor, in fact, you can see in Selberg integral, this is the n square log n factor. So this one, I can take it outside and absorb inside this overall factor, which I don't care. I'm just interested only in the lambda dependence. So then you just have this. So there is a factor n which explicitly appears here, such that now if you do the same analysis for typical lambda I twiddle, you see that this guy will be n times lambda square. So this guy is of order n square, and this is also of order n square, and therefore they are correct order basically. Okay? So that's why it's usually done, and you will see that it actually is convenient to do this rescaling right in the beginning. So from now on, when I write my potential, and this is the same exercise if it is arbitrary v lambda I. So in that case, you just replace this guy by v of lambda I twiddle. Okay. In general, that's the convention. So I'm just using a factor n explicitly here to, and then I'll forget about this lambda I twiddle, and in general, I'll call them again as lambdas. Okay. So I've just done a rescaling, and I'm just looking at the rescaled gas with the convention that my coupling here is, I just multiplied a factor of n in order that both terms of the same order. Okay. So you can say this is your starting point. Okay. So my convention is going to be put a factor n in the external potential term so that all the lambdas are of order 1 typically on the steps. Okay. So now my energy, I'll call E of lambda I with this convention of this. Okay. So the step 1 is define this counting function. I'll just put a hat here to notice that this is a random variable. This is not the average. Okay. So I'll denote rho n hat lambda average as rho n lambda. Okay. This is not a very good notation, but this is a random variable which is just defined as so in a given configuration, this function just counts. So if you have a charge like that, discrete charge, so how does this guy look like? So this guy looks like, it just is 0 everywhere, except when you are plotting as a function of lambda in a typical configuration. So it picks up a delta function here, and then it will like this, 0, and then delta function there, and 0, delta function there. So it's called the counting function. It just counts the charges, okay, with a factor 1 over n outside, such that this overall thing is always normalized to unity. So the weight of each delta function is 1 over n. Whenever there is a charge, it picks up a factor 1 over n. Okay. So the advantage of defining this function is the following. So now note that if I take any arbitrary function f of lambda I and sum over I equal to 1 to n, so that will be just n times integral rho n hat lambda f lambda d lambda. Is that obvious? Just substitute this formula here. So the n will cancel, and when you integrate this delta function from each I, you will pick up of f of lambda I. So therefore, this you get this sum. Okay? This is a trivial identity from the definition, but this is going to be very useful. So valid for any function. So this is step 1, definition. Step 2. So step 2 is what is called the coarse graining system. You have heard again this word before. Sumit said that in his field theory lectures, coarse grained system. And I'll tell you what it means exactly. So coarse graining. So coarse graining has 2 micro steps, if you like. Okay? When I write this explicitly, you'll understand. Okay. So fix rho n lambda. Number 2, sum over all micro states consistent. I'll explain to you. First, let me write down. And I'm doing it for here, but it's a very general thing. If you have any interacting many particle system, you can actually do this coarse graining this way. And then step 3 is a sum over or integrate over all possible rho n lambda. Let's keep this in mind. So what I'm doing here, I wanted to keep this guy here. Okay? So then I can erase this part. So what this step 2 means is the following, that I'm taking this partition function, this multiple integral. So I'll write mathematically these things that I wrote down there. This is the energy. So let me explain now. So what did I do? So I want to do the same multiple integral. I'm rewriting the multiple integral in a slightly different way. How? So I'm saying that, okay, first, think of so even though for finite n, this will be like this delta function, But in the large n limit, this will be a smooth function, somewhat smooth function. Okay. So I first fix the function. Okay. So if I fix the function, by definition, this function is exactly this. Okay. So I can just put a delta function over this object here, and then integrate over all possible functions finally. Okay. This object, you see, this d delta n. This is a functional integral that Sumit wrote down. Okay. So what I'm doing is the following. Roughly speaking, this is called coarse graining. Okay. So I have these charges, lots of charges. Okay. So I'm just defining a smooth function, which is the density. Okay. So I first define this function, this density. Okay. I sum over all possible microscopic configuration charges. Okay. Consistent with this density. So think of this part first. I'm just doing a partial tracing over all possible microscopic configurations which are such that this delta function constraint is satisfied. Okay. So this object here is, so I'm fixing rho n lambda, and I'm summing over all possible microscopic configuration consistent with this given rho lambda. Okay. And then finally, I'm integrating over all possible such things. So this is one particular form of the function, but I could have, used another density. So I have to sum over all possible functional choice with the constraint that they are all normalized to 1. Okay. So all I'm doing is, by multiple integral, I'm doing it in 2 steps. Okay. So first I fix overall density, and I sum over all possible lambdas consistent with that density, and then finally I sum over all possible densities. Okay. So that's so this is exactly identical here, and this definition of this d rho n lambda is precisely the functional integral that Sumit defined. Okay. So you can think of discretizing them, and it's a sum over all possible these things. Okay. So just sum over functions. Think of sum over integrating over functions as opposed to integrating over variables. Okay. So I didn't do anything. I just wrote down. This is all you have seen that when you do renormalization group, you do exactly that. Okay. So and this is exactly what Sumit was doing also. So I just do it in 2 steps. Okay. Fix first a coarse grained. This is called coarse graining. Okay. So coarse graining means that I fix the overall density. I sum over all possible microstates associated with that density, and then I sum over the densities. Okay. The 2-step process. It's called partial tracing. Block spin, for example. So in Ising model, that's what you do. For example, you divide into blocks. You sum over all possible spins inside a block, and then you sum over all the blocks. Okay. So that's exactly what it is done. Yeah. Is this clear to everybody? Any question on this? Okay. So once you have that, so what did I achieve by that? Okay. So then step 3. I'll remove this. Express basically the energy which is in terms of the lambda i's. Okay. Now we try to express the energy in terms of this smooth function rho n hat lambda. Okay. Can I do that? Yes, I can do that. So I just take this guy and I just use this identity here. Okay. This is true for any function f of lambda I. Okay. So for instance, the first term there, so I can use this identity here to write this as n square v lambda rho n hat lambda d lambda. Okay. The second term is a bit tricky. The second term is what? So j not equal to k log of lambda j minus lambda k. So what I'll do here, so here there is some physical assumption will go on, because in order to pretty well define this system when you are going in the continuum limit, you have to define some kind of lower cutoff, because the charges cannot sit on top of each other, right? The probability for that is 0 basically. Okay. 2 charges cannot be at the identical place. Okay. So in any configuration, typically you will never come to a situation where one guy is on top of each other. Okay. So there is always a lower cutoff or distance basically. So I'll call this as delta I. Delta I is the shortest possible distance between charge I and I plus 1. Okay. So if that is so I can actually write this in 2 steps. So I sum over all possible jk. I mean, this is just taking the continuum limit carefully, okay? Minus so what does it mean? So here, j is not equal to k, so that is ensured that these two will never be equal to each other, basically, okay? But so what you do is you add in the j equal to k term, but the interpretation is that the minimum value of that is actually delta I, okay? They can be a maximum closest, even when the two coordinates are equal, there's a spacing between them, basically, okay? So you write down this, so I just wanted to write this as jk, and then you subtract off this term, which is, so this is called, I mean, in the field theory language, this is called the self energy. Okay. Yeah. So last step, I mean, all I'm saying is that, see here, j not equal to k, right? Now, I want to write it as sum over all j and k, not just j not equal to k. So I have to include the j equal to k term. But if I put j equal to k term, this is divergent, right? So all you are doing is put a small cutoff. Okay, you said I'm allowed to do this, but when lambda j equal to lambda k, this is log of 0, which is divergent. Okay, so you are subtracting off the infinity from this, saying that okay, lambda j minus when j equal to k, when two charges are very close to each other. Okay. So the minimum distance can be of order delta, basically. Okay, so you're just putting a cutoff, basically. You're saying that, okay, I mean, in the continuum limit, I can be as close as possible, except that I just have to subtract off when they are exactly on top of each other. Okay. The reason I'm doing this because, I cannot use this identity here when j is not equal to k. But when j equal to k, I can use this identity and express this guy in terms of the density, okay? But then I have to subtract off, there's a, divergence. So this is always the field theory, basically, okay? In continuum field theory, you have to always subtract off infinities, okay? This is the whole idea of renormalization, basically, okay? So anyway, so you subtract off this infinite term here, but for the moment, you just assume that there's a small cutoff in the theory, okay? Huh? Yeah. Yes, this will be linear because all I'm doing is that, okay, how do I put it? I mean, in the sense that for each charge, I'm saying that this charge, imagine this, for each charge, you have a little, finite area around this charge, which is the delta I, okay, little length. Imagine charge rod, basically. Okay. So you're supposed to think of that way, okay? So from each charge, I'm just, separating out some kind of self energy. And then, this part, I can again use this object, but sum over double sum, basically. And you can write down this as a double integral, okay, over lambda prime, okay, in the continuum. And this guy here, so delta I, what is the typical spacing between charges? Delta I is roughly 1 over the local density of charges. Okay. So some constant, and this constant, when you take the log, this constant you don't care. So effectively what happens is that this term here just becomes sum over I, so log of rho n lambda. Okay. So this is a sort of approximate way of taking care of self energy, essentially. Self energy means that when two charges are on top of each other, there is a huge infinite repulsion. So you want to take into account in a way so that and this term here again I can use this formula there. Okay, so this is rho n lambda. Yeah, just 1 minute. What did I do? Sorry. Okay, let's just look at the self energy term here. Okay. I can use this identity again to write it as okay. So overall, what I have is that, so there is this term here, which just becomes plus n rho n hat lambda log rho n hat lambda. You have to sit down yourself, okay? Just don't try to follow online. You have to just sit down and do it yourself, and then you will sort of realize that this will be true. Okay, so what did we do then? So I wanted to evaluate this energy, express it in terms of rho n lambda, and I managed to do that. So what I have that the energy itself, the reason I'm doing it in gory detail here, because this is very useful when you do try to do any interacting particle system. You can actually use this procedure, and you want to do large n limit, then this is a very general problem. Okay, so this is the first term here, this guy, okay? And then I have the second term there, which is minus and then I had another term, self-energy term, which is minus n rho n hat lambda log rho n hat lambda d lambda. So what you find is that this guy here, I'm able to express it in terms of the local density. It no longer depends explicitly on the little lambda is. Okay? So what that means, I can take out this guy outside this multiple integral. Okay, so this is the step 4. So you notice that this is just a functional of rho n hat lambda. It does not depend anymore on the little lambda is. So I can just take it outside this integral. Okay. So then what I have is that and I'm left with only one integral here, which is okay. So I have to do this integral. But this integral has a very nice physical interpretation. Remember that this picture that I was drawing here, coarse screening. Okay? So I have this overall density profile, and I'm summing over all possible lambdas consistent with this density profile. Okay? So this integral now here, so this is times this. So this integral here, what does it say? It says that how many microstates are there. I'm summing over all this, so all possible microstates. So how many microstates are there consistent with a given density? Okay? And you know from statistical mechanics that this is exactly what we call the entropy. So you see how is it coming? So there is an energy term, and there will be an entropy contribution from this, because entropy means basically how many microstates are there, consistent with a given density. Okay? So you have to evaluate this entropy term now, and then we are left with one functional integral, which is the field theory, basically. Okay? So let's evaluate this density, the entropy term. Yeah. See, all these approximations are going to be exact in the large n limit, okay? So what's the simplest way to evaluate this integral here, entropy term? So the idea is the following. So imagine that, very simple calculation. So imagine that you have n particles. So if you put these n particles, so you separate, imagine that, just breaking your system into m boxes. Okay? So you separate your system into m boxes, and so you have to put n particles in m boxes. You have to distribute them in such a way that the density locally is some given number, given function rho n hat lambda. Okay? So therefore, the total number of particles, so if I say Ni is the number of particles, so think of again box and balls, okay? So number of balls, so number of particles in the ith box. So I have m boxes. I put my balls in these boxes. So therefore, the total number of particles is just this. So how many ways can I do that? Okay, before that, so this is the coarse-grained picture, okay? So, and the Ni, which is the density, which is the number of particles in the ith box, okay? So divided by n. So this is the fraction of particles in the ith box, okay? So what you would expect is that what you want to do is that you want to fix this to your given rho n lambda. Okay? So if basically I'm looking at a given lambda, and around this lambda I'm constructing a box basically, and I'm putting Ni number of particles there. So locally this is the local fraction, okay, local density. So that is given, that this is the constraint, okay. So I have to distribute the particles in such a way that my locally Ni over n is some given number. So a number of ways of doing this. How many ways? Anybody? Number of ways of distributing n balls into m boxes. N factorial over n1 factorial, n2 factorial, nm factorial. Agreed? Everybody knows this. So what I'm saying is that now this n factorial will be, okay, I'm just with the abuse of notation, I just say n1 factorial means n times the density at box 1. Okay? This is n1 factorial. n2 factorial will be n times density at box 2 factorial, and so on. Okay. Now I'm interested in large n limit. So what will you do in the large n limit? Starling's approximation. Very good. So Starling approximation. Which says that roughly speaking, L factorial, if L is very big, goes like e to the power L log L minus L. Okay. So now you can do Starling approximation for the numerator and also for each term of the denominator. That's why I wrote n times this. So that n is large, this is of order 1. So I can use Starling's formula to approximate them, large n. So if I do that, so I'll just, so what do I get? So I get e to the power n log n minus n in the numerator, and the denominator I get again e to the power summation n rho hat of box I log n rho hat at box I minus n rho hat I, sum over I. So therefore this is exponential n log n minus n, and the denominator I can take out this n log n factor, okay, So basically what you get is, okay, you can check this. This will be e to the power n log n minus n times e to the power n summation I rho I hat log rho I hat. Okay. You can use the fact that summation rho I hat is 1 actually. By definition. Okay, so then you're done. So this factor cancels up there, and so it becomes exponential minus n, and now I can replace this sum by the integral. So this means rho hat lambda log rho hat lambda d lambda. Okay. So as you pointed out correctly, that the entropy term looks almost similar to the self-energy term, but they come with a different prefactors, as we'll see. So basically what we did here is to evaluate this term. So if I call this term as I, then all I'm saying is that I, this integral, effectively has this behavior in the large n limit. Okay? Very good. So then you are done essentially. So what is the final result then? So I just want to put everything up there now. I have this E and I have this guy from here. So therefore my partition function Zn in this large n limit after this so-called coarse graining then I have this energy term. Beta by 2, the energy term. And the energy term is, okay, I can write down explicitly, we have written down somewhere, yes. So maybe I'll just do this, n square. It's very big and maybe boring, but you know it's actually useful. Okay. Plus, now I had a term. So energy term I wrote down this guy, but I have not written down this guy yet. Okay. So and what I can do is that this guy will be beta by 2 minus 1. So you can check that this will be where does it come from? So the entropy term, so minus e to the power minus n times this is just this entropy term. Okay? And there's a self-energy term which was coming from this term. So remember energy is e to the power minus beta over 2 times this. So that minus, and overall there is a minus. So therefore this beta over 2 times n times that is a self-energy term. Okay? So this is the self-energy contribution. And this is the entropy contribution. Okay, so that's what your field theory is. So there is a field theory with an effective action, which is the energy and the entropy term, entropy and self-energy, whatever. And this is the main interaction energy. And there's a constraint that now you have to sum over all possible densities which are consistent with the fact that they have to be normalized to 1, because that's what by definition you use that. So the point is that, so unlike in the usual stat-mech system like Ising model, as Kavita was saying, you see that here the main energy term, okay, is of order n square. And the reason is because of this, repulsion between, it's long-range system. Long-range system is never extensive, okay? So because of the pair interaction, so therefore this is of order n square, okay? But you see the self energy and the entropic term is of order n. In equilibrium stat-mech like Ising model, they are always comparable. Energy and entropy both are extensive, okay? But here in this system, long-range system, what you see is that the energy dominates the entropy, okay? So this is always of order n square, and this is always of order n, provided this beta is of order 1. See, if the beta becomes order 1 over n, which happens in some problems, but I'll not spend on that, so then it can be comparable, because if beta is of order 1 over n, you see this term becomes order n, and this term, there's a term here which is of order n. So therefore, the entropic contribution matters when beta is of order 1 over n. Okay? So here you cannot throw away the entropy term. So always you have to be careful when one throws away the entropy term, okay? Just to be sure that it works. But anyway, for us, beta is of order 1. So in that case, I can safely throw away this term. So I did a lot of things to calculate this, but in the end I won't need that. Okay. But it's important to know that there is always an entropic contribution to the energy, okay, when you are writing the coarse-grained field theory. And but it so happens the entropy term or the self-energy term is always extensive, that means order n. But the interaction energy or the interaction with the external potential, the main part of the energy is always order n square, and therefore it dominates the action compared to this guy here. Okay? So this is the sort of main conclusion. Okay? And you notice that one other small point is that beta equal to 2 is always a special in a unitary case, because then this correction term is exactly 0. Okay? But of course you can have other correction terms here, a constant plus order 1 over n and so on. This is what I'm doing is a large n expansion of the action basically. I mean, we'll see later Sumit will also do large n expansion of nonlinear sigma model. It's a sort of similar spirit here. Okay? So in the large n limit, so the first correction term disappears only for a special value of unitary matrix. Okay? So this has the implication in field theory. I'm not going to discuss that basically. But for us, actually, we can generically throw away the correction term because we are saved by the fact that this is of order n square and this is of order n. Okay. Which minimizes this action with this term here. That is the one which will be dominant in the large n limit, because all the other guys will have a value of the action larger than that, and therefore they will be negligible. Okay, they'll be sort of killed because of the large n. So basically, you are going to pick up in the large n limit. You are going to pick up the contribution mostly from the density that minimizes this action. Okay, so this is the heart of saddle point method. But I have to take care of these constraints. Okay? So you all know how to do that. So formally what you do, I mean, normally you do when you minimize something subject to some constraint, you've all learned that you have to introduce a Lagrange multiplier, right, which usually fixes this constraint. Formal way of saying that is what I can do is to replace this delta function by its integral representation. So if you have any delta function, let's say delta of y, let delta of x minus a. Okay. So there's an integral representation of this, which says that this is just dk over 2 pi exponential ik x minus a. Okay. So because your idea is to somehow raise it as an exponential, okay, and then you can use everything in one action. Okay. So if I do that, so I start from this, and then I just write down this as functional integral over all possible integrals, and this delta function, I just replace it by Um, and from here you notice that you can actually make a weak rotation in the, you can, this is k is real, but you can also write k as complex and write this as dk prime over 2 pi I. So just make a rotation. This is called the weak rotation. This is like what Sumit was saying when we were going from Euclidean to Minkowski time. It's a similar thing basically. Okay. So I can then use it like this. So k prime is just a dummy variable basically. So just replace this delta function by this integral representation of the delta function so that the density has gone in the exponent. Okay. This is just another way of saying Lagrange multiplier. So let's just look at this how it gives times beta by 2n square into this action here. Okay. So let's call this I don't know what we want to call it. Let's call this guy as E of rho n at lambda. Just a name. Okay. So, and typically, okay, I mean, so basically it says that you have now, okay, I mean, actually for some reason I'll just call it, denote by mu naught instead of k prime. Okay. So what you have then is okay, I can put everything here, 2 pi I is not very important. So you can write down this as e to the power minus, okay, I had this k prime, okay, and what I'm going to write down is k prime, just to make it this comparable to this. I can always do that, okay, I just rescale, and I write k prime as beta by 2n square times, let's say mu naught, where mu naught is the new variable. I make a change of variable. Okay. Then I can write down everything as b by 2n square into some action which depends on this rho n hat lambda and this parameter mu naught. Okay. So what is this action? Let's write down. So this is our E of rho n lambda, energy term, minus or plus mu naught rho n hat lambda d lambda minus 1. Okay. So you see, this is exactly what you do when you do Lagrange multiplier. Lagrange multiplier simply means just representing delta function by its integral representation. So you have this, and now when you look for saddle point, you have to minimize with respect to rho n hat lambda, and you also have to minimize with respect to mu naught. And when you minimize with respect to mu naught, you see that gives back this condition here. Okay? So you can think of this mu naught as a kind of Lagrange multiplier. That's the whole idea of Lagrange multiplier. I mean, when we learn in the school, it's taught us as some kind of mystery thing, but this is the main point behind Lagrange multiplier. Lagrange multiplier simply means that when you have a constraint, means you have a delta function, and you just use the integral representation of the delta function, and when you minimize with respect to the saddle point thing, then automatically the action has this object here. Okay, very good. So we have the action now. Okay. Where E of rho f lambda is this guy. So what do we have to do now? So as I said, saddle point approximation means that I have to look for minimize this action with respect to rho n hat lambda and with respect to this mu naught. So what does minimization means? The saddle point equations. So this is a functional derivative. And the second equation is del S del mu naught equal to 0. But this guy will give you back the constraint itself. Right? When you derive with respect to mu naught, it just gives you this constraint back. So the important information is in this saddle point here. When I do the functional derivative, so I take this guy here. So this is the same as del E okay, because sorry. So I want to take the functional derivative with respect to rho n lambda of this action here. So first I take the, with respect to E, del E del rho n lambda. So that gives me a V lambda, right? I'm taking functional derivative with respect to rho n lambda. So it picks up at lambda the value of the potential V of lambda. And here if I do it, so you can check that this will be just minus 2 times rho n at lambda log plus mu naught. Plus mu naught comes from this term here. When I do functional derivative with respect to this, I get mu naught. So this should be equal to 0. So why there is a factor 2 here? Because when you take the functional derivative with respect to lambda, lambda comes here, and then this guy, when the second argument also can become lambda, so there is a factor 2 which comes in here. Okay. So this is so my saddle point density, that is the density that minimizes this action in the large n limit, is I call it rho hat star. Okay. So this rho hat star satisfies this saddle point equation. Okay. Now this is a very simple interpretation physically. What does it mean? So you notice that this is nothing but basically the statement of energy conservation. Okay. So if you think of these charges, okay, so suppose I have, sorry, this should be lambda prime. Yeah. So if I have a charge at lambda prime, okay, let's say I think of a charge at lambda. Okay. So this is the external energy which it fills, and it also fills the logarithmic interaction due to the interaction energy with the other charges integrated over lambda prime. So that gives you this interaction term, and the total energy is conserved per particle, and that is just a constant term here. Okay. So now I have to solve this equation and satisfying the constraint that rho n star lambda d lambda equal to 1. So this is where the technical challenge is. Okay. So at least we are done. We have started with a multiple integral, this guy. We reduced it to a functional integral, and then we are now taking saddle point of that. And the saddle point density is this. So that means my charge system basically roughly will settle down into this particular configuration. So I need to find out what is this particular configuration. What's the solution of this integral equation? Of lambda square if you want, simplicity, and they are repelling each other by charges. Okay, so first thing you notice that is it possible that this rho n star lambda, the best density, equilibrium density, is it possible that it can go all the way up to infinity? Is there a possible solution without solving this? Okay, and what I want to say, okay, so take the example of simple case of Gaussian, let's say. So then the equation is something like this. Now, if it was extending all the way up to infinity, okay, you will be in trouble. Because why? Because this guy here is growing like lambda square, okay, the energy, potential energy. Now, if this lambda prime was going if the integral was from minus infinity to plus infinity, okay, then you see that for very large lambda, this term behaves like, so very large lambda, I can, just throw away the lambda prime here. I can, just do an expansion, let's say, just this guy as log of lambda 1 minus lambda prime over lambda, which I write down as log of lambda mod minus log of plus log of mod 1 minus lambda prime by lambda. So I'm doing a large lambda expansion. So the most dominant term for large lambda will be just log of mod lambda integral rho n star lambda prime d lambda prime, which by definition is 1. Okay, so therefore the second term for very large lambda here is behaving like log of modulus lambda if your integral was going from minus infinity to plus infinity. Okay, main point is that this equation holds for all lambda belonging to the support of, you know what support is? Support means that if you have a function which is non-zero, roughly speaking, okay, if you have non-zero, let's say over a to b, then this a to b is called, this interval is called the support of this function, where it's non-zero. You can have, you can think of a function which is non-zero here and then becomes 0 outside exactly. In that case, we will just say the support of this function is a to b. Okay. So, if this equation is something like that, then I'm saying that this equation holds because you are doing functional derivative with respect to rho n lambda, which is non-zero. So therefore, this equation holds only where the density is non-zero. Okay. So within the support of this density. So if your support was minus infinity to plus infinity, the whole real line, then you see you are in trouble because this guy here, this term, second term is behaving like log of modulus value of lambda. For large lambda, it goes like log lambda. But this guy goes like lambda square. And this guy is a constant. So you will never be able to match them, basically. That means there is no solution. You cannot have a solution with infinite support. Okay? So first thing that you learn without even solving this, that if you have a confining potential which grows faster than log lambda, okay, like lambda square or lambda 4 or whatever, I mean, you cannot have the solution with infinite support. Okay? It has to be a finite support. Okay? So that's the first conclusion. Okay? But we don't know what the endpoints are, A to B. Okay? So let's look at the Gaussian case first. Okay? So I know that it has to be from A to B, some finite support, and let's assume that it's a single. So physically, we would expect the charges to be, somewhere here, concentrated here. Okay, so it should have a density like that. So let's say A to B. Okay, so this is the energy conservation equation. So what I can do now to make further progress, I can take one more derivative of this equation with respect to lambda. So this is lambda belonging to AB. This is very important. So if I take derivative with respect to lambda, then you get lambda, or in general, more generally, you will get V prime of lambda. Let me write the general thing. So if it is a V of lambda, so I take a derivative with respect to lambda. So there is a V prime of lambda minus 2 A to B So what did I do? What is this? So this term is very simple. I derive with respect to lambda is V prime lambda. This time when I make a derivation with respect to lambda, so it gives you lambda minus lambda prime, the log term. But you see that the system can diverge when lambda becomes equal to lambda prime. So actually, when you take the modulus, logarithm of modulus derivative, so this means principal part. Everybody remembers what is the principal part of an integral? you have an integral like that, let's say, I don't know, something like that. Okay, take any arbitrary function, f of z dz. So what does it mean by principal value of the integral? So it means that, okay, I'll do it this particular case. Okay, what this means? Okay, principal value of this integral. So this integral diverges in the lambda plane, in the lambda equal to lambda prime equal to lambda, right? So what you have to do is we are varying this lambda prime. So there is a lambda here where there is a divergence. So principal value means you go from whatever, your lower limit up to lambda minus epsilon, and then from here lambda plus epsilon. So you break the integral into 2 bits. And just take out this part from around the divergence point. Okay. So this is the meaning of the principal value. Okay. So because of the logarithm of mod, this thing, there will be always a principal value which will come in. You can check because of the divergence of this. Okay. But again, this has a physical interpretation, because this is like this was the energy conservation condition, but this is like a force balance condition. Because this guy here, or minus of that guy if you like, is the force that a charge feels, V prime. V is the external potential, so this is the external force that it feels, and this external force is being balanced by the repulsive force from all the other charges. Okay? So that, as I told you, the external potential is trying to drive the system towards the origin. Okay? So that force gets balanced by the repulsive force from the other charges. Okay? So this is the physical interpretation of the saddle point of this equation. Okay? So we need to, somewhat like that. Principal value is always, this log of lambda. If you want to do it rigorously, you have to put in that, keep in that delta and do it. You could do the same thing with discrete lambda i's, but it's this is a much nicer way of doing it basically. Okay. So now the technical challenge, main problem, is how to solve this. So these integrals, in mathematics there is a name for these kind of integrals. So these are called Cauchy singular integrals. Okay, they are not so easy to solve. Okay, so this is generally this is a technically, mathematically, this is the difficult problem. Okay, however, so, and I'll not prove it, but I'll tell you the result. There is a beautiful result due to an Italian mathematician called Tricomi. There are 2 ways of solving this equation. So I'll first tell you the first way, and maybe in the next class I'll tell you the second way. So this Tricomi actually found a general solution to the following problem. Okay, so here I just divide this by 2 and write half times that. So explicit solution. So you see what we are doing, I mean, just think of this, I mean, electrostatics. So you do electrostatics, okay? So you can think of, it's not, the electrostatic analogy is a bit vague here because of this principal part here, because your charges are sitting on a real line. So, but roughly analogically, so electrostatics, I give you the charge density, and you evaluate this, effective electrostatic potential. So this is like the electrostatic potential, which is in 3 dimension. It's like the net potential due to all other charges. Okay, but here it's like an inverse problem. Here, so usually, I mean, if you open any electrodynamics books, like Jackson's book, for example, there, usually Jackson gives you the charge density and asks you to calculate the potential. Okay, But electrostatic potential, don't confuse this V lambda as a potential, I mean, as I was telling you for the particles. This term basically, this is like a phi, if you like. Phi is like a electrostatic potential. But here it's like a reverse problem. Here, this is something you know, because, this for Gaussian random matrices, this is lambda square, for instance. So therefore, this term is just lambda over, just lambda, okay? For Gaussian case, phi lambda is just lambda. So here, you give me the potential, and I'm trying to evaluate what is the charge density that gives rise to this potential. Okay, so this is like a inverse problem of electrostatics. Okay, so roughly speaking, inverse okay. So the explicit solution of trichomy, I will write down but not prove it. So in general, this trichomy theorem is the following. So you have Gx So if you have a Cauchy integral equation like this, so principal part going, and if you have, if you assume that there is only one single support a to b of your function, yes, a single support, that's an assumption. Because you could have imagine a situation where you have multiple supports, like 2 supports, 3 supports, but you are going to assume, because physically it's clear that the charges will be only one single support, only one single blob basically. Okay? So therefore we assume that single support, and in case you have a single support, and suppose this is this is what you call this is what I was calling phi of x, okay, if you like, call phi of x. Okay. So this is your electrostatic potential. So whatever be the value of phi, function phi of x, so what you want to do is to invert this equation and express rho as phi, basically, because phi is given to you. So the explicit solution of trichomy for the single support case is the following. So A and B are the endpoints of my support, okay, and A is less than B. This is a beautiful theorem, very useful. There is a famous paper by, Breza, Itzikson, Parisi, and Zubair, and they spent a long time solving similar integral equation problem, because in their case it was a lambda fourth potential, lambda square and lambda fourth, so this will have a cubic term. Okay, so this is a very famous paper of Itzikson, Parisi, Zubair, and Breza, and they spent a long time in trying to find the solution, and which was nice because this gave rise to a new method which is called the resolvent method, which is more like a physicist method. But actually, they need not have to solve this problem if they knew about trichomy. They did not. Okay. So trichomy was much before, of course, but they did not know the explicit solution of trichomy. So they spent a long time in solving that problem. That's a very famous paper, but it's a good, it's a useful paper because it gave rise to a new method, which I'll have, if I have time, I'll talk about next lecture. Okay. So this is the solution, inversion formula. Okay. Sorry, this is phi of x. So I have phi of x, I want to calculate rho x. The inversion formula is precisely this. So you have 1 over pi square root of b minus x times x minus a minus 1 over pi principal value of a to b square root of b minus x prime minus a divided by x minus x prime phi of x prime dx prime plus some arbitrary constant. So proof of this is very difficult. It's not so easy to prove. So I will not go through this basically to the proof. But these days Mathematica can do all the integrals. Okay, if you do this to the Mathematica with some simple function, it can calculate the objects. So let me just write down some simple results using for this principal integral, which is quite useful when you evaluate these kind of things. So for instance, if you calculate a to b, you can check with the Mathematica. All of you know how to use Mathematica, right? It's good fun. So for instance, if I choose phi to be 1, okay? So then I have to evaluate this integral. And this integral, you won't find this in Gradson, Reisig or standard books, but you have to do it by Mathematica. So they're very simple formulas. Okay. Another one which is useful is of lambda over 2, so which means v prime of lambda. So I took v lambda to be lambda squared. Okay, so v prime lambda is 2 lambda divided by 2, so 2 cancels, so it's lambda. Okay, so phi of lambda is linear, so here you have x prime. So I can use this identity here. Okay. And I can, so this is, so in my case this will be rho star, okay, the saddle point density. So first thing you notice that, okay, another thing I forgot to mention is that in this large n limit, you see that the n dependence has gone away. So which means that it just says in large n limit, this becomes independent of n, okay. So n has gone away from the problem. So if I just evaluate 2 lambda square plus some constant C1. So I just use this result there, okay, and just rearrange a little bit and you will find C1 is another constant. Okay. So I have these 3 unknown constants, A, B, and C1. Now I have to use the symmetry of the problem. So what is the first symmetry? The first symmetry is that you have in your problem for Gaussian potential, you have a lambda going to minus lambda symmetry. Okay, which means that if this is lambda equal to 0, so your density must be symmetric. It must be the same for positive and negative lambda. Because your potential is symmetric and the charges also maintain the symmetric. You have a lambda going to minus lambda symmetry in the problem. Which implies that rho star of lambda must be same as rho star of minus lambda. Okay. So which says that you can't have a linear term here. Okay. So immediately you see that B has to be equal to, or A has to be equal to minus B. Okay. So I can talk about minus A to A. Or minus B to B, sorry. So now I have only 2 parameters left. So if I use B equal to minus A, so it just becomes 1 over pi square root of B square minus lambda square times C1 minus lambda square. The C1 must be equal to B square. You can cancel the square root of this. He of course didn't use any of these things, okay. He just guessed, okay, the solution of the integral equation. He did not know about the trichotomy or anything, so he just guessed. Okay. And but funnily, even if you look in Mehta's book, he doesn't talk about trichotomy. Mehta's book, by the way, Mehta's book is a very famous book in random matrix theory. Okay, so everybody uses that book. But if you go open that book, you would not find trichotomy because he didn't know about trichotomy also. And in his book, he just uses this integral equation and then he says, try this solution and see that it works. So he doesn't derive it, okay. But the trichotomy is great because it's really gives you for arbitrary this thing, it gives you the solution. And this has been, we have last few years, I don't have time to talk about this. I mean, we have used this trichotomy theorem quite extensively for solving many problems in random matrix theory. So it's really, really very useful, okay. So, here I just demonstrated it just for the case of calculation of rho star of lambda, which is the density of states. And so that's the first, important explicit result in random matrix theory, if you like, that it says that the average density is so the charges would like to settle down on a semicircular thing. So basically, after you have rescaled your original this thing by n, okay. So then, for the Gaussian case, it actually, the density actually approaches an equilibrium form in the sense that in the large n limit, it becomes even independent of n once you have rescaled this way. and it's given by this particular form. And the beautiful, which I'm not going to prove, but nice thing about the semicircular form is that it's actually very, very universal, in the sense that it's very difficult to prove, but like central limit theorem, if you take the Wigner matrices, for example, with independent entries, not necessarily Gaussian, okay, they take uniform distribution, for instance, okay. You cannot calculate the joint distribution of eigenvalues, but it turns out that if you actually look at the distribution of the average density of states, it's always given by the Wigner semicircular law. Okay. So with a finite variance, basically, if your sigma square of the individual distribution of the entries is finite, it's actually so these are the results that mathematicians have proved, that essentially that Wigner's semicircular law is very, very, very general. Very universal in some sense. Okay. So, and that what really is important, that the fact that it goes to 0 as a square root singularity. Maybe we'll have time to discuss about that implication of that, but that will be in the next lecture. So I think I'll stop here.